Agora eu vou chamar ao palco Rajat, Kumar.
You can start over, you can run free, you can find another fish in the sea, you can pretend it's meant to be, but you can't stay away from me. I can still hear right to the ground, taking me down, we rolling the ground. You can pretend that there with me, but no. Baby, I'm praying you tonight, let you down into your life, just like animals, animals like animals most. Maybe you think that you and I can smell your feel from miles, just like animals, animals like animals most.
Thank you. I love that song. Okay. Cool. Let me just get this full screen. Okay. I can't seem to find the toolbar. Where exactly are you? Okay, this is much better. And Yep, no worries. And I think I got it. Woo! Well, hello everyone. That's the formal hello. How is everyone doing? Come on, that was so low on energy. You guys just had a break. Come on, how is everyone? Yeah, that's much better. That is what I expect from BrazilJS, folks attending BrazilJS. So, welcome to my talk, Conditional Modules and Dynamic Bundling at Netflix. It's a Netflix original story. So, is there anybody here who doesn't know what Netflix is? Oh, wow. Everybody seems to know what Netflix is. This is awesome. So, you know, Netflix is an online video streaming service, and we have like so many shows, so many movies, documentaries, Netflix original movies, Netflix original documentaries. And what is pretty amazing about Netflix is we are available in 190 countries. And we have over 140 million subscribers globally. So, hashtag Netflix everywhere. So with that, I would like to start. My name is Rajat Kumar. I work at Netflix. I am part of the Node.js platform team, and we build Node.js libraries. We build infrastructure that other engineers use to build Node.js services, and then these services are consumed by the UI and the product team. So today I am here to talk about the bundling of JavaScript files, especially at Netflix, and how we challenge some of the common conventions to solve our set of problems related to bundling. All right, so this talk is actually split in 4 parts. So I'm going to start with the problem statement. I'm going to try and explain what exactly we are trying to do and why exactly we are trying to do. Then we'll talk about how we broke that problem down to actually get to the solutions. And finally, I'll end the session with some of the future things that we want to accomplish. So Netflix, again. So Netflix is a data-driven product development company. When I say data-driven, all I mean is we do a ton of A/B tests, like hundreds of A/B tests. Okay? And when we do these A/B tests, as an engineer, we always design our applications keeping these A/B tests in mind. And all the data that we gather with these A/B tests, we use that to evaluate what works the best for our subscribers. What's the best user experience that people actually enjoy? So for example, this is a Netflix.com. This is the Netflix.com website. So when you log in, you see something like this. And as UI developers here, probably a lot of you would be able to recognize that, hey, this particular UI is composed of several components, right? And what we do at Netflix is we A/B test almost everything. So here you can see we might be A/B testing, let's say, the category title. We might be A/B testing how the images should show up. And at times, some of our tests are as minute in detail, like the Netflix logo right there. Like, where exactly should it be on the image? So we literally run hundreds and hundreds of A/B tests. And what happens when we run these A/B tests? Well, what happens here is that with each A/B test, there is a possibility that each subscriber actually gets a unique and a different user experience, because the UI just varies based on which A/B test cell you fall in. And I would like to point out that it's not just the fact that it's A/B test that will change your UI experience, also the fact that which device you are accessing it from. So the Netflix.com website and the TV UI app that we have, both are built using React. But if you access it from your television, it's a different user experience. But if you access from your browser, it's a different user experience. And as a matter of fact, if you happen to be between Chrome or Firefox, you might still have a little bit of different experience. And it's all because of the devices that we use. So now let's start with an example, OK? So I've highlighted the search box. And let's assume that we are actually running an A/B test where we want to A/B test the experience of search. And for simplicity, let's assume we have two components. We have a current search experience that we want to show, and the new search experience that we want to show. So as an engineering team, it is our responsibility that we actually bundle together all the JavaScript code and send it down to the devices so that both these experiences actually work, right? So you might think that you can actually imagine that the code would something be like this. So the JavaScript modules are like broken down. You have app.js, which is the actual entry point. And then you have two different search components, like the current search component and the new search component. And all of them have their dependencies and sub-dependencies. So we are actually delivering all of these files, OK? And what happens here is if you happen to be in the current search A/B test cell, then you will get the current search component and its dependencies and sub-dependencies, because those are needed for current search experience to work. Likewise, if you are in the new search experience, you will get the new search component and its dependencies. So as an engineer now, again, the code would look something like this, especially in app.js. You would just say, hey, I'm just going to import my current search, and I'm also going to import my new search. And then somewhere in that particular code, you have this if condition, and you are only rendering one of the experiences or one of the components, right? So that's the way most engineers do it. What this also means is because you just imported two experiences in the same file, the package actually contains all of these files, right? So do we see a problem here? Well, of course. The problem here is we are actually packaging two mutually exclusive code execution paths. And we know for a fact that only one of them is ever going to be executed. The fact is, at Netflix, our apps are already way too big. If you actually take a look at the source, we have so many files and so many lines of code. And when we start putting together all these different experiences and knowing the fact that only one of them is ever going to get executed, the bundle sizes could be as big as 10 megabytes for website and almost as big as 30 megabytes for TV UI. So now just imagine delivering this 10 megabytes of file over to the browser. I mean, as a customer, I would never like it. So what happens with this is you see slower performing apps, and of course, the time to being interactive increases drastically. So at the end, what we see is really, really poor user experience. So what exactly are we supposed to solve? Like, how do we solve this problem of user experience? So the common convention here says, we should be building smaller packages. Just build those smaller packages which are specific to, let's say, all the A/B tests that user falls into, and deliver those. But can we really do that? Like, can we actually build really smaller packages tailored specific to a user's A/B test? Well, it turns out it's not an easy problem to solve. Because of the fact that Netflix runs hundreds and hundreds of A/B tests, we actually have some side effects of that. Actually, we have to think of the bundling in a slightly different way. And let's see how that works. So at Netflix, we run A/B tests. And most people think of A/B test as having typically two variations, a variation A and variation B. But at Netflix, what we do is we have multivariate A/B tests. So that means one test can potentially have multiple variations. And it's not just multivariate. We actually have multiple multivariate tests running at the same time. And we are just trying to collect all the metrics around these different test cells and figure out which one works the best for our users, which one actually makes brings joy to our customers. How the users get allocated to these A/B test cells, it's totally random. So it's like, as long as you satisfy certain criterias, you might get added to those A/B test cells. And when you get added to these A/B test cells, and because they can be random, that means every user gets a different view of the same UI, slightly different experience than each other. So the next question that comes to mind is, this did not flip. Yep, and we're back. Second time is a charm. I'm sure it's going to work now. OK, so the next question that we had was, OK, how many packages do we really need to build and serve? Any guesses out here? Like, with hundreds of A/B tests, how many packages there would be? OK, well, the math here is pretty simple. It's the number of items in each test multiplied by each other. So basically, what we are saying is it's a Cartesian product of the number of variations that you might have in each of the test cells. Let's simplify this a little further. So let's assume we only have 15 A/B tests. And these 15 A/B tests have 4 variations each, right? So what that means is basically it's 4 into 4 into 4 15 times. So that's 4 to the power 15. Any guesses what this number would be? Well, that's over 1 billion. So with just 15 A/B tests, we are talking about serving like billion different combinations of packages. And now think about the fact that what happens if there are hundreds of A/B tests. Well, the fact is 4 to the power 100 is like, it's a very big number. I don't even know how to pronounce or even show it on the slides. Well, so essentially, mathematically, we know now that we are planning to build and serve like billions and billions of packages. So at this moment, the problem statement should be pretty clear to you guys. So we are planning to serve billions of smaller packages, and these smaller packages need to be specific to our users' A/B test allocation. But again, the next question is, can we really do this? Can we really build like billion packages for every build, every push that we do? Well, at this scale, it is pretty unreasonable to do it all. So what happened was we wanted to solve this problem, and we got very serious about solving this problem. We dressed up like Jessica Jones, Luke Cage, the defenders of Netflix. And oh, by the way, I'm the guy in the suit. So we were very serious about solving the problem. And what we realized over time was, hey, you know what? We actually have a server, and servers can be fast. Node.js is supposed to be fast. We are all great JavaScript developers. I'm pretty sure we can build something that works for everyone. So we were actually thinking about and talking about building all these bundles or packaging all the files together at runtime on a server. So what we did in our search for the solution, we looked back. We looked back at how people actually write their code. And what we figured was, most of the times, developers just keep like a simple Boolean value. And all these experiences are actually just gated behind these Boolean flags. So for example, when new search experience is true, that's when you want to show the new search component. And similarly, if it's false, you just want to show the current search component, right? That's the simple logic that most of the times we have to deal with. And we thought a lot about it. And we said, you know what? If we can build a system that can look at the code and figure out all such conditions within the code, maybe we can speeden up the bundling process. Like maybe it is possible to actually bundle everything together on the server. So we broke down our problem into two spaces. One was the build time, and the other was the request time. So at build time, the idea here was what we will do is we'll look at the code, we'll figure out all the conditions, we'll do all sorts of static analysis against your code, and then use that information, give it to the request time. So anytime somebody requests for a package, just use this previous existing information, bundle stuff up together, and deliver. Sounds easy? OK. So what we did was we chose Node.js for our request server-side basically technology. And on the build side, we decided to use Webpack. We chose Webpack because Webpack actually has all the right hooks, and it actually gives you pretty good options to customize the behavior of the build process itself. Plus, we also liked the fact that it has great ecosystem of plugins, and the fact that most developers are actually comfortable using Webpack. They understand how Webpack works. So that made kind of pretty much sense for us. So now we started working on those solutions. And on the build side, our process would look like, we have this Webpack-based build process, looks at your source code, and then it generates an output file called an artifact. And this artifact actually has all the metadata needed to say, this is your dependency graph. So these are exactly the way your different files are related to each other. And it also figures out all those special Boolean conditions that it sees. And on top of that, it also keeps a copy of all the optimized and probably even transpiled source code. So you can think of this artifact as one big snapshot of your source repository with additional information. And then at the runtime, what we planned to do was, OK, we'll just give the same artifact to the server. And then anytime a request comes to the server, just read that artifact, get all the information, bundle the files together, and send. So this is exactly the system that we ended up building. But before we actually go deep in, let's understand a few more concepts around here. So as we saw in the build step, we are generating this artifact. And this artifact is pretty important because it acts as the bridge between the build side and the request on the server side, right? So it is pretty important to understand what goes inside of this particular artifact. So what is it supposed to be? Well, to start with, obviously, this artifact needs to have the dependency graph of your source. So something like this, right? Additionally, we also figure out all the different Boolean conditions that we see in your source code. So that means we are also storing the dependency relations with the special conditions, right? And finally, we also need to make sure that all your transpiled and optimized code is existing in this artifact. And to do all of this, we are relying on Webpack. So what we want Webpack to do is, hey, you know what? Can you please build the whole conditional dependency graph? Can you extract all the metadata? And at the end, can you serialize it into a file? So that was the goal. But doing this, we came across several terminologies like, what is a conditional module? What's a conditional dependency graph? What exactly is a condition? So I'll try to explain that with this example. So in this case, app.js should include new search only when the condition, which is the new search experience, is true. So in that case, what happens is we consider the new search experience, the Boolean value, as the condition. And all the dependencies and sub-dependencies, including the component new search, becomes a conditional module for us. So essentially what we are saying is app.js can only import new search when the condition is true. So the next question that we have is, how do we mark these files as conditionals? And how do we make sure that Webpack actually understands that these are the dependencies or these are the files which are conditional? So what we did was we introduced a special syntax. So one of the first special syntax that we introduced is the @condition comment. So what this says is, hey, the new search.js file can only be included if the condition new search experience is true, right? And because this is a special syntax that we kind of enabled with Webpack, Webpack is able to understand this particular syntax and then identify all the list of such conditions. The second syntax that we use is the $conditions.newSearchExperience syntax. So all this means is that if it is true, if this particular condition is true, you can import new search. If it's false, you can import the current search, right? So this is, again, a new different kind of a syntax that we introduced. And we built our Webpack setup to kind of understand this. So now we understand that, OK, this is how we provide conditions. But how do we build this conditional dependency graph with Webpack? Well, the answer here is pretty simple. What we do is we built our own Webpack plugin. And what this plugin does is it relies on the different Webpack hooks to figure out what needs to be read and what can be ignored. So what we did was there is this parser.program hook that Webpack has. And it gives you the AST, or the abstract syntax tree, for the file that it's reading. And our plugin would then look into this AST and figure out if it matches any of the syntax and maintains the list. The next thing that we have to do here is we have to go, again, serialize all this information. And again, for that, we just relied on the emit hook of the Webpack, and we just wrote it down into a file. So at this time, what we have is we have a Webpack build which has conditional dependency graph information in it, and we just serialize it into artifact. So we solved the first part. Now coming back to the second part, which is the bundling as a service. So at Netflix, we have bundling. Our bundler, or our on-demand bundler, is called Codex. So you can imagine that if somebody makes a request from the browser, that request actually comes to Codex. So it's requesting for that JavaScript file from the Codex servers. And this particular server is able to give back the JavaScript file, which is very specific and highly targeted for that particular user. So the next question you should have is, how do we resolve these conditional dependencies at runtime? Well, the secret sauce for our server-side component is the URL. So if you see the URL at the top, it's a templatized URL. And this URL has all the information that our servers need to go and start resolving all the files. OK, so for example, you can see this particular URL says, hey, this is for the web UI app, and I'm looking for version 3 artifact. Once you have that, please make sure that you can unlock these two experiences. So these are the conditions, which is like at the tail end of the URL, comma separated. And then Codex is able to understand also the fact that, hey, the entry point mentioned was app.js. So it starts to resolve the dependency graph from app.js. And it keeps looking back at what are the different conditions that are true and that can be actually used to resolve. And then finally, once it's resolved, it just sends it back. The resolution algorithm is simple as well. So for example, in this particular case, you can see that there's a fork right there. And the resolution will move only in the direction where the condition is true. So in this particular case, the new search experience is true, so it moves down that path, and it will only stop once it again reaches a conditional edge. So something like this. So at this moment, what happens is you have two different conditional edges. One is smart playback, and the other is smart session. And we can see in all the list of experiences that can be unlocked, you can unlock smart playback. So what the resolution logic does is it ignores smart session, and it includes smart playback. So what has happened is the whole dependency graph has now been shortened into a much smaller graph, and this is what we use to bundle up and create the package and deliver. So at this point, you might be thinking that, hey, isn't this process really, really slow? Well, it is not. So we have worked a lot on optimizing the graph resolution logic. As a matter of fact, we have also improved upon how we store the artifact information. We have multi-level caching to do that, and a lot of memoization for the graph traversal. And that actually helped us bring down our latencies to be like less than 70 milliseconds. And this is for the website app. For the TV UI app, it's close to 300 milliseconds. But then that's also good. The other interesting part about this URL is the fact that this URL is self-contained. So in the sense, if you provide the same input, Codex is always going to generate the same output. So that means we can use the same setup to be, the bundles can actually be cached. So we are actually fronted by a CDN in this case, and we never process the same request again. Everything gets served by the CDN. So in summary, we talked about two different syntaxes that developers use. And then the Webpack build runs. It identifies your conditional dependency graph, generates an artifact. And this artifact is then consumed by our Codex servers. And when a request is made to our Codex servers, it comes through CDN to us. And Codex generates the bundle, stores it, caches it on CDN, and then it's sent to our users. So that's exactly the system that we built, and that's all the different components that we have. So now I'm just going to talk about some of the new features that we are planning to go for. And the most important, and actually it's one and the most important for us, which is the developer experience and the Webpack. So what has happened because of our system is you cannot use Webpack's default dev server, because now there's an artifact in between, and obviously Webpack's dev server doesn't understand that. So we are still trying to make it compatible with Webpack's dev server. So that's one. And the other thing that we have is the fact that we still do not have source maps available. So that's been a problem for our developers, and that's exactly what we are working on next. So that's all for now. Thank you so much for having me here. And please feel free to reach out to me if you have more questions. And I'm available on Twitter as Rajat Kumar. Thank you so much.